Hello, everyone. Right now, I'm going to be giving a talk on data privacy with Apache Spark on defensive and offensive approaches for it. I am Serge Merton, a resident solutions architect at Databricks Amsterdam. And in the past 13 years, I've been working on all stages of the data lifecycle. I've been working with Apache Spark for around 6 years now. I was building data science platforms from scratch. I tracked cyber criminals through massively scaled data forensics. And I also created anti-PII analysis measures for the payments industry. My full-time job right now is to help and bring that work to customers to the next level in their AI journey. What I expect from viewers of this talk. Most likely, all of you should have a hands-on background in data engineering and Apache Spark, some information security, and a bit of cloud infrastructure. Virtually a bit of everything. You want to, or you're asked already by your bosses, to limit the data to maintain privacy and complying with regulations like GDPR and CCPA. If you don't know about them, we'll briefly cover that also. And of course, you should have a genuine curiosity about how to do this. So this presentation is about tools for data privacy when it comes to artificial intelligence journey, like in this slide. But in this talk, we'll be talking only about data privacy. We'll try to use hints for the thing that's called open source intelligence, which is essentially looking at all available information from all available sources, including those that are open on the internet. Please look at this fancy link that you see on the slide to know what kind of information you can find just lying around online. So here, like one of the typical offensive techniques you see here on this right and the right, which is known as day-to-day data science. So in reality, data science is performing link attacks. So what you see here is a botnet that operates by what it seems two different criminal groups, but in fact is the same organization in the center, offering command and control centers. Threat intelligence analysts are looking at the graphs like this every day. Later, during tokenization section, we'll show an example of a sequence attacks. And in data rollup slide, we'll touch on homogeneity attacks. So what is personal identifiable information? Emails, names, addresses, zip codes, IPs, account numbers, driver licenses, you name it. It depends on the nature of your business. Some of them have stricter regulations, some of them not. Your mileage may vary. Talk to your GDPR and CCPA trusted advisor on the matter and make a plan on action. And by the way, you need to be aware of all anonymization techniques, which you may be able to build yourself. So we have plenty of techniques, but all could be divided into categories of pseudonymization and anonymization. One is on the record level and is mostly used for machine learning. According to GDPR, a pseudonym is still considered to be a personal data. Given the right access, process, and tools, you can re-identify a pseudonym to the original value. This is quite complicated to make in practice. And by the way, if you want to have a nice and accessible user interface for re-identification, you should buy third-party products. I haven't seen anyone making one very nice from scratch. So on the screen's left slide, you see typical examples of synonyms, just gibberish letters. On the right hand, we have anonymization, where the scope includes entire tables, databases, or even the enterprise data catalogs. This is usually for less restricted business intelligence aggregate tables. Usually, there are more people in BI than data scientists, and they don't need record-level access, so they work with anonymized data. Data scientists cannot work with full anonymized data because it loses its value, though in some companies they have to. It depends. Frequently, a combination of more than one pseudonymization and anonymization techniques are used. Let's dive deeper. So the first one is encryption. When someone thinks that Amazon S3 or Azure ADLS encryption at rest is not enough, the accuracy of data is high. It's medium difficult to implement. Schema is mostly the same. Performance is going down when you write data. It's slower to read, and it adds up on the cloud cost. Here's the example with AWS key management service encryption. With ADS, KMS, data keys decorator, it reads a key from the config supplied by a Terraform example. On the next slide, it creates a UDF, and the wrapper function initializes Amazon encryption as the CA client. And it makes a data encryption key from the customer master key. Pandas UDF is executed in the Python subprocess with efficient arrow serialization. By default, the subprocess is reused, but you can disable that by Spark Python worker reuse false at forking performance cost, of course. This way, you can guarantee that data key decryption is happening in dedicated process for a given Spark task. This is to make security officers happier. Later, here you see we call the .apply method on Pandas series to change each row's values for that specific encrypted column. Here you see a simple Terraform configuration that initializes the instance profile, registers it with Databricks, creates the AWS key, and grants the generate data key and decrypt permissions role that instance profile is tied by. It creates a cluster where it is specified that this cluster will be using that specific EC2 instance profile that has access to the key that encrypts or decrypts the data, which you pass as a Spark conf. It also installs the PyPy library for Amazon encryption SDK. You can use the previous functions slides easily. It's effortless, and in practice, you just reuse the things. As you can see, original data point is small. Encrypted data is 50, 60 times larger than fake name of a non-real person here. Consider if you really need it, if you have data at scale. Most likely you would need to use different pseudonymization techniques for your organization. So data architects will probably be watching this to try to make an informed decision. So the other technique is hashing. Just apply SHA-512 to everything. Yeah, just hash all sensitive data that way. Accuracy is very high. It's elementary to implement, and schema style is the same. The format is different, but it's a bit bigger. It hurts group by statements. And for example, if you hash the email and want to know the number of unique people in our imaginary e-commerce shop geography, the more bytes email address will have in memory, the slower the group by would be. It has risks of malicious re-identification. There are many attacks like dictionary combinators, or there's a brilliant tool called Hashcats, which is a very advanced one because it uses GPUs and a broad community of good and bad users. So to make cracking a bit harder, what you generally do is create a salted hash by prepending some random data to original value, usually in the beginning or in the end, or both. You're then applying the hashing algorithm on top of it, that's all. My advice could also be to encode the hash with base 64 instead of a hex encoding. You'll save approximately 33% of the space, have some security by obscurity, and make it way easier to store on the storage and have a bit quicker group bys. It's also easier to pronounce this base 64 hash than full length SHA-256, because you'll see it copy-pasted or told about and shared between your employees a lot. Databricks is a lovely functionality that replaces each secret, like a hash salt, with redacted word, essentially anonymizing it. It's only meant, though, to be used against incidental printing, just in case. But anyway, do not try to reinvent the new salting technique. It's probably already cracked by a hashcat. The background on this slide shows the algorithms that the hashcat can figure out. So one of the common things that I'm seeing in every company is a free-form data, which is a text that might have an email, a personal name, or some IP address, or whatever. Generic solution is hardly possible. Recommended is the ensemble of different techniques that remove sensitive pieces out of free-form context. One of the techniques could be having a regex rule set to filter out emails, IP addresses, and whatever. Another thing, what you need is probably addition of named entity recognition, which doesn't really work on short strings, but works on bigger than 5-word sentences. What can also work is pip install names dataset, which can get you 160K different names that you can use as a filter. And here's the example how to do that in the Pandas UTF. Enhance these names with definitions with more region and business specific data, and you will have a lovely way to strip the private information from the free-form data. The general rule: if you cannot efficiently replace the free-form data from your big data lake, just don't put it there. On the other hand, you can have an offensive use for names datasets, and it's called combinator attack. Essentially, you take all of the first names and all of the last names, join them together, and in the end, you get 16 billion records, almost a terabyte of data, and then you can build the reverse lookup table. Same data, different use, good use, bad use, so it depends. You're applying some background knowledge attack in this case. Like the key space for cracking the personal names is really small. Like we have approximately 6 billion people in the world. And of course, we can guess the names of everyone, but we can use different tricks like trigrams. So the trigrams for my name, Serge, are SER, ERG, and RG. Then randomly combine those in the proper sequence, and you'll probably guess the names. Probably put in some Markov chains on top of that, so you get more fancy results, a smaller number of random records, less brute force, and whatever. Anyway, this is a common technique to fight against typos, and it's very simple to implement. Yeah, still, this is research. If you want to invest in it, do that. The type of data that can be considered very, extremely sensitive is credit card numbers. So here we have 4 rows. The first row is PAN, personal account number. The one you see is a fake credit card that can be used to test Visa payments, and it's found online. It's available to everyone. Yeah, sure. But it doesn't work. You can make payments with it. So this is what payment card industry data security standard scope protects. Do not store it in plain text ever, period. It's not legal. So the first, or it's not good. If you store credit cards in plain card text, you will have to have way harder security measures for the data storage. So the first 6 digits of a credit card number, usually 6 digits, called bank identification number, or BIN. And there are approximately 6,000 different ranges of those available in open sources. Sometimes it's the first 6 digits, sometimes it's more, sometimes it's less. BIN is not sensitive by itself. The last digit is used for number integrity validation. The last 4 digits is what you commonly see in all user interfaces about your cards. And that's the only thing your bank might ask you on a phone call to name the card. Otherwise, it's a scam. It's not recommended and sometimes not allowed to store both the first 6 digits and last 4 digits of a card on the same record. Guess why? Rules are very convoluted and sometimes contradictory. Bottom line is, don't use hashing for credit cards. Use tokenization instead. Tokenization has very high accuracy. It isn't easy to implement, and the schema is almost the same and the format is different. Whatever the value is, it's stored usually in a type long number. It's slow to write, but it's way faster to read because you have fewer bytes to shuffle around. Usually, with tokenization architecture, you have the highest access control level for the anonymization layer, mandatory to be in a separate subnet, in a separate network, whatever, which has the token vault database, which is called that way because it's the most sensitive thing that the infrastructure has. So that token vault host types of data and their values with their numeric representation. All of the sensitive data should live there, just more compliant and more well-defined. You'll see why it's easier to have this architecture. So how to implement tokenization? Let's look at the step-by-step way how to do the token work. We get the columns and turn them into the array of structs. Once you have the array of structs, what you have to do is explode them and do star struct pushup. Once you have that, you select the key and value and then assign a token. In this case, a row number, ordered by ID. So Reynolds, a fake person, will have a token 1, and his email is going to be token 2. Well, look at the order. The email and name of the same person. It's sequential. So you can even guess the name when having the email, or vice versa. Making randomly sorted window and getting our row number within that window fixes that. Tokens are available on the same record, but the records are not vulnerable to sequence attacks because tokens are far apart from each other. The previous slide is vulnerable to sequential attacks, and this one, no. This is just the example. It would help if you stored a token vault somewhere, which brings Databricks Delta into play. It's one of the options to do that. So you have to deal with Delta's eventual consistency model. On the code example on the right, there are same functions from the previous slides, but what you also have here is the retry loop in which you are trying to save the table again and again if you get concurrent modification exception. We're not using certain functions that come across in mind usually, like monotonically increase in ID or UAD type 4, because they either don't work as you expect, don't perform, or hard to merge into Delta Vault. So simple technique, simple answer is use Databricks Delta, use the sample codes, and be more compliant. It's easier to do GDPR or CCPA with vault-based systems. You have a single place to delete sensitive data, and without a vault, you have to perform data erasure operations on probably thousands of tables. Because if you have big data, if you are in the need of the token vault, then probably the number of different distinct datasets is huge. So one of the typical usages for anonymization techniques that I'm saying is a synthetic data, which is randomly generated dataset for external datasets. The hardest part is to make data looking real and respect real-world skews and distributions. Another thing is perturbation or noise. Look at the technique of synthetic minority oversampling. And this algorithm can actually make a statistically valid perturbation for your dataset that you give out externally, or for your own data scientists if you don't trust them. Like, it makes it a bit more anonymous and adds differential privacy. Usually, this technique is not used on its own. So the easiest way to deal with anonymization is to suppress, not display, the data by making a row-up. Whenever we see a certain threshold with a minimal amount of records, some background information about it. So you know the country's biggest cities and you know the country's smaller cities. It's a piece of background knowledge. And imagine you're working for an imaginative retail company and you're analyzing some key performance indicators per that region. If you see the smallest city popping up with just a few records, you can find out information about people living in it. Just look up on Facebook, LinkedIn, or other places. People usually tell where they work publicly, or what they do publicly, or where they live publicly. If they don't, yeah, they are very caring about their privacy, but mostly people don't. So, and with that, you can more or less reliably guess how much money those people are making, and then the list goes on. The other thing that is common is a generalization, where, let's say, there are different genres of music. For example, there is technical death metal and there is mathematical grindcore, which really can define a person because this is a very specific piece of information. If you want to anonymize it further, you can generalize it one level up. And instead of mathematical grindcore, black metal display extreme metal. And it's also not too private enough. So you'll tell a person likes rock music. If it's not private enough for you, you can just suppress the column of a music taste and don't display it at all. So this is one of the typical examples of generalization. You can apply it to other data sets, but you get the gist. The other thing is binning. So take approximate percentiles of data, let's say 3, and split them into, let's say, by the join dates and the tenure of people, split employees into new, seasoned, senior, and early employees. You did, as you see on the slide, a very simple and rapid clustering with Spark, and you don't need a classify algorithm for that. You can do that with a pure SQL and it will perform very quick because it's approximate percentiles. You don't need concrete percentiles for this. Some of the data sets require special truncation rules. So let's say for IP addresses, take the last byte from it, replace it with 0, and you got /24 CIDR. Especially, essentially, you're generalizing the data to the city level or so. It's safest actually to store the IP addresses in /24 if you want to give them to data scientists, or even /16, but that is not so useful anymore. So yeah, you can apply rounding to data. And there are some rules that are general, like rounding numbers to nearest multiple of 5, 15, 25, 50. Any numbers of half that are rounded or suppressed. Halves are always rounded upwards. Let's say 2.5 is rounded to 5. So your organization needs to implement your own rules for rounding because it might be more or less sensitive and it depends on the business. Only at Databricks, you can protect the data on column, row, and table level without requiring any external product. So there is column level permissions. There are row level permissions and table level permissions that work on high concurrency clusters. They're a bit more expensive, but you don't need to get the external product for that, which makes overall data management way easier. Watermarking is a fun case. Accuracy is very high on the snapshot. Essentially, it's a tokenization applied to the query. It works only for a snapshot. It makes no sense globally. It's designed for that. You need to write the catalyst rule for that if you want to have watermarking with Spark. So the schema is the same, and what you end up doing is storing excessive amount of different token vaults. Think of security challenges of this. And it gives you an exciting opportunity to track if your data has leaked outside or not. Because you can tie a token to a person that received a snapshot. You have a mapping for that you store on your infrastructure. And as you see, it isn't easy to operationalize, and it should be applied only for the most sensitive data. And when you really don't trust your data scientists. The other things would be related to external controls. When you need data scientists to track different data scientists, and you also need to track data scientists that track data scientists and things on. So auditing, it requires significant infrastructure investment. Like you can do a very simple one, you can do a very complicated one. The things to focus are on usage patterns and ordinary filters. You alert on outliers. And you can use Databricks audit logging and Amazon CloudTrail, deliver to S3 buckets, add some processing magic to it, and correlate the data yourself. Use some Azure audit logging service. Like Good luck with that. It isn't easy. But if you're working in the regulated industry, you need it, and you'll probably have to do it. Another option is remote desktop to prevent copy and paste of data and make life of your data scientists more difficult. You can give any access to the data within the remote desktop, because basically you have the online web interface that accesses the data, but you can access that web interface only through the remote desktop. So you can essentially give more distinct data accesses over there to this mechanism. But you can have a screenshot of it or a photo shot by your phone or something, especially in the COVID times. So there is a very non-COVID-19 friendly way to do that. If you want to prevent people from taking screenshots, you should require a physical desktop, which is a 10 client, to a remote desktop with a Windows desktop on it, with a motion sensor camera that detects attempts to take photos. That's also probably requires giving away your phone and keys and being hand searched before you enter the workspace. And one of the banks is doing that. If you don't trust your data scientists at all, you can too. But it's an overkill, in my opinion. So thank you all for a very productive session. This was Serge Smerting of Databricks Amsterdam. And please make sure to leave the feedback and apply the knowledge you've gained in this session later afterwards. Thanks all.